All right. So today I'm going to talk about this fixed parameter, the practical fixed parameter algorithms for defending Active Directory style attack graphs. And so this is co-authored with a master student, Jialiang Li, and also Anita and Frank. They're part of the audience, and also Han, who is a cybersecurity and a network researcher. And he basically introduced this problem to us. And the problem is a cybersecurity related application problem. But at the end of the day, the way we approach it is just treat it as a graph-based combinatorial optimization problem using fixed parameter analysis. And we also throw in a little bit of graph convolutional neural network just toward the end. But then the important parts are the fixed parameter analysis part. And this paper, this is based on one paper that was published in AAAI 2022. And I will also briefly mention some of the recent progresses that are based on papers that are in submission. All right, so what is this problem? And basically, from the get-go, we try to study this very applied practical problem that is we are talking about a Microsoft Active Directory environment. And essentially for every large organization or small organization, as long as you have multiple Windows machines, then chances are you have an Active Directory environment. So most likely your university, as well as our university, University of Adelaide, we are using Active Directory to manage user accounts, security credentials, and everything, etc. So this is the default security management system for Windows domain networks. And then somehow this problem actually is exactly a graph-based problem. The thing is that, all right, so this is for Windows, basically a security management system written by Microsoft, the default one for Windows domain network. And it's actually because it manages accounts for most organizations worldwide, it actually receives a lot of targeted attack from attackers. So for example, there's one survey that says that in the last 2 years, there are about like 50% of the organizations, they experienced the Active Directory-based attacks. And this is probably an underestimation because maybe organizations got attacked and they don't even know. And I mentioned that, I mean, for most of the audience here today, you probably care more about like the underlying algorithmic design problem. And then this Active Directory environment actually naturally describes an attack graph. And an attack graph is basically a graph involves a whole bunch of nodes. And then the nodes would represent accounts, computers, security groups, and etc. And a directed edge from one node A to a node B would represent that an attacker, if the attacker has access to A, the attacker can then later on access B via either existing access from A to B or via an exploit that allows the attacker to go from A to B. So basically the attacker can just like traverse on this directed graph and then just jumps in between accounts, computers, and etc. in order to basically perform the attack. And this is actually a model, even though this is a theoretical computer graph-based model, this is actually used in industry by real attackers and the real defenders. And on GitHub, there's one software tool that actually made this graph popular. And this software tool has 6,000 stars. This is written by a security company. And the paper was the tool was originally motivated by this paper that was written by Microsoft Research, but then this paper has been sitting there for 5-6 years without getting noticed, like many other academic papers, unfortunately. And until one day, this security consulting group, they just like made this into a tool. And then this tool would model a specific kind of identity snowball attack under the Active Directory environment. And here's one visualization. So the attacker, suppose initially the attacker compromises one account, for example, by sending out a personalized phishing email, and it gets into account A. And then this attacker can just use an existing access. For example, suppose account A already has access to computer B, the attacker can then jump to computer B. And then this is another node. This is a directed edge. And then from this other node, the attacker can actually scan the memory, and inside the memory, we have the password of account C. And there's one relationship called has session, which means that account C has recently logged on to computer B, and therefore there's actually password inside the memory. So this is basically based on an existing, basically a known exploit. The attacker can just travel from another node to the third node, all right? So essentially the goal of the attacker is just start from some initial compromised node and then try to reach the highest privilege account that's called the domain admin. And then the core functionality of BloodHound is actually to automatically generate the shortest path from the attacker's entry node to the domain admin. Okay, well, the distance is defined as the number of hops. So basically the main functionality of this tool is that the attacker can, you enter the internal network using one account, and then the attacker can just like run this tool. This tool would just like map out the whole directed graph, and then this tool would actually tell you, you should do this first, then do next, and etc. And here's the shortest path where you can reach the domain admin. That's the main functionality of this tool. All right, and then generally, the reason this tool uses the shortest attack path is because, well, longer attack paths imply higher chance of failure or higher chance of getting detected. So we study defense via edge blocking. The idea of edge blocking is that we can possibly cut some edges. So for example, like ban account A from accessing computer B, all right? So that would be cutting this edge. Or we could just like add monitoring. That's another way, like in some sense, that's also blocking edges. So this idea of blocking edges is actually practically used by real defenders. And also the original paper that motivated BloodHound was also talking about like some heuristics for blocking edges. And our goal in this paper is just to basically figure out the optimal edge blocking policy, and the goal is to prolong the attacker's shortest attack path length. All right, so that's basically the motivation of this paper. All right, one moment, please. All right, so oops. So here's the formal model description, and we adopt a two-player Bayesian Stackelberg game setup with pure strategies only. Now, if for those of you who are not familiar with the game theory terminology, this is actually not, I mean, fairly easy to understand. Essentially, the idea is that the phrase pure strategy means that we are only considering deterministic blocking. We are not considering like randomized blocking. And then this Stackelberg game, the meaning is that we would lay out the defense and we assume that the attacker can actually figure out like which edges have been blocked, and then they would avoid the blocked edges to perform their attack. And once again, this is actually consistent with we believe it's consistent with reality because the attacker can actually scan the network to figure out like which edges actually disappeared. Okay, so an AD graph is a directed graph with a whole bunch of nodes and a whole bunch of edges. And in practice, this graph is huge. For many large organizations, we are talking about tens of thousands of nodes. So for example, let's say consider any like a grade A universities in Australia, we probably have tens of thousands of computers in the network, and then tens of thousands of accounts and etc. So the network is going to be huge. And then the attacker would enter the graph via one of the S entry nodes. And the entry node is selected by nature according to a fixed distribution. So the idea is that I basically hope to model it in a way that basically this is to model how the attacker enters the network, often via a phishing process. The attacker would, for example, send out mass email to a whole bunch of accounts, and eventually one would took the byte and then click some link. And then, so basically that's how the attacker can reach one entry node. And that's according to basically some kind of a distribution determined by nature. And then the attacker's goal is to reach a single destination node, which is called the domain admin. And then there's a set of edges that are blockable. So not every edge is blockable because some edges I may actually need it for the normal functionality of the organization. And then the defender picks B edges to block, where B is a constant defensive budget. So essentially, like we assume that we can only block a fixed number of budgets. So once again, this is very common in combinatorial optimization, but in terms of, for example, practical application, the motivation, one motivation example I love to use is that suppose whenever I block one edge, I need to do a little bit like auditing. I need to generate a report and write a whole bunch of emails to inform the relevant parties and etc. Suppose it takes 1 hour to do this task. And every month I have 1 day dedicated for this type of job. And then that would be a budget of 8 edges that I can block. All right. So that's basically an example to motivate why we have a fixed budget. And then the attacker plays the best response. After we block some edges, the attacker plays the best response by attacking via the shortest attack path. So for example, the attacker is just using the BloodHound tool. And then the attacker's chance of success is fx, where x is the length of the shortest attack path, while f is non-increasing and f infinity is equal to 0. Well, we actually use f to represent the chance of success. And a longer attack path means lower chance of success. And then no path at all means a 0 chance of success. And we assume that f is given. Okay. And then the goal of the defender is to minimize the attacker's expected success rate, where expectation is taken over all the possible entry nodes. So for example, suppose there are 100 accounts, let's say 100 email address listed on the organization's front page, then maybe we could assume that every account has 1% chance of being the one that is the entry node. Okay. And here's an example Active Directory attack graph. So let's take a look at this example. And we have 3 entry nodes. So 10, 11, 12, they are the entry nodes. 0 is the domain admin. And then the attacker would enter, for example, via one of these nodes with 1/3 chance. Okay. And then there are some intermediate nodes. The attacker would basically try to, for example, if the attacker enters here, the attacker would attack this way. Okay, that's the shortest path. And the thin edges are blockable, and the thick edges are not blockable. And suppose our budget is 2, we want to select 2 edges to block. And then what would be the best way to block? Well, if we select 2 edges to block, we just block this one and this one. We block 3.1 and 3.2. That would completely cut away, basically all the entry nodes are completely cut off from the domain admin. All right, so that's the, in this simple example, it's very easy to see. If the budget is 2, what would be the best way to cut? Okay, if the budget is 1, I wouldn't cut either this or this. If the budget is 1, I would cut one of these 3. So if I cut this, then, well, 1/3 of the chance I actually am able to defend against attacker entering here. And then 1/3 of the chance this guy has like a uninterrupted route. And then 1/3 of the chance this guy has uninterrupted route. Okay. But so basically with budget of 1, it's to block one of these 3. And then they are all optimal. Okay. So now it turns out that this problem is difficult. Computationally difficult. When there's only one entry node, even if there's only one entry node, our model reduces to the well-studied shortest path edge interdiction problem, also called the most vital edges problem. And that was proven as early as 1995. So this is an NP-hard problem. So we basically, it's NP-hard to figure out the optimal edges to block. And then, but the above NP hardness result does not rule out scalable algorithms for practical Active Directory attack graphs, because we're not talking about general graphs. An for example, the Active Directory graph is not going to be, for example, special graph like a bipartite graph. It's not going to be, anyway, so it's not general. It has specific structures. So we could possibly just exploit these specific structures in order to derive efficient algorithm. So that's why our approach falls into the category of a fixed parameter analysis. Now, for those of you who are not familiar with fixed parameter analysis, the idea is that we are dealing with NP-hard problems, but then if we assume that the actual instances are easy, we assume that the actual instances that we need to solve are actually described by a few parameters that are small. Then basically small parameters correspond to easy instances, and we try to develop algorithms that specifically exploit the fact that there are some parameters that are small, and we can then derive scalable algorithms for practical purposes. So what will be the parameter for active directory attack graphs? And here is one synthetic active directory graph generated using the BloodHound team's synthetic database generator called DB Creator. And we just generate basically this DB Creator would just generate a synthetic active directory graph. Basically, it would specify, for example, in which nodes, what's the name of that user, what is the department that user belongs to, what's the operation system used by that user, etc. But we care about the graph topology. So we care about the graph structure. If I plot out this synthetic active directory graph involving 500 computers, the graph looks like this. And we immediately observe two things. First of all, the attack paths are very short. So for example, from one of the nodes, it takes only like 1, 2, 3, 4, 5 hops to get to the domain and mean. And another thing is that the graph is very similar to a tree. It looks very similar to a tree, but unfortunately, it's not exactly a tree. If it's exactly a tree, then the problem actually is trivial. Okay, so we basically make these two observations, and that's the foundation of our selection of fixed parameters. And the first parameter we look at is the maximum attack path length. And we assume that the maximum attack path length is small for even the largest organizations. And according to basically the BloodHound team's original words, they basically try to compare this phenomenon. They also observe this, and then they compare this phenomenon to the 6 degree of separation for the small world problem. They basically, essentially the idea is that all people in the world are 6 or fewer social connections from each other. So basically we make the observation. This is not a proven fact. We cannot prove it, just like the small world observation. It's just something we assume it's going to be generally true for practical Active Directory graphs. And we also, that's basically for a parameter for describing maximum attack path length. And then another thing is that we want to describe, basically we want parameters that would describe that the graph is close to a tree. And then there are two parameters. One parameter is tree width, which we will get into. Tree width is a commonly used parameter in fixed parameter analysis to describe how close a graph is to a tree. And another thing we actually use is the number of feedback edges. And then our definition of number of feedback, basically our definition of feedback edges is as follows. It is considered the best practice for AD graph to follow the organization chart. So for example, marketing would form one tree branch, and a human resource form another tree branch. But then it's not exactly tree because marketing, someone in marketing may need to access some computer from human resource and vice versa. So it's gonna be a tree with a whole bunch of security exceptions. And then that security exceptions basically are the non-tree edges. And then those are what we call, in this paper, the feedback edges. And that's basically, we assume that the number of feedback edges is small. That's another parameter for describing the tree likeness of the AD graph. And then another parameter is budget, another parameter is the number of entry nodes. So these are the parameters we are going to use in fixed parameter analysis. Okay. Sorry. We first showed that having a small maximum path length alone does not make the problem easy. We then propose 3 fixed parameter tractable algorithms. The first, basically, they have different complexities. I'll go over them briefly later on. And then finally, for one of the fixed parameter algorithms, we are going to convert it to a graph convolutional neural network-based heuristic. And a fixed parameter analysis is a very powerful complexity analysis tool, but then the parameters may not be small enough in practice. So for example, here, H is the number of feedback edges, the number of security exceptions in this AD graph. And then here, our complexity is 3 raised to the power of H. So you can imagine that this H needs to be very small, as in 20, right? So for example, if it's 30, it's probably too difficult. So, but then I would imagine for a large organization, the number of exceptions is much larger than 30. So this algorithm actually doesn't scale unless we're talking about tiny organizations. Now, in order for this algorithm to scale, we resort to a graph convolutional neural network. A typical FPT approach is to exhaustively search among a set of solutions characterized by the parameters. So searching over 3 raised to the power of H scenarios, that's too large. So we cannot search for that. And instead, we use a graph neural network to guess what would be the best solution. So essentially, this comes down to a combinatorial optimization problem with a sequence of decisions that we need to make. And then we just use graph neural network to guess, to train it to guess better. And so at the end of the day, we are not indeed exhaustively searching over all the solutions described by the fixed parameter. We're just trying our best within our computational capability to find the best solution as we can using graph neural network. And then so our neural network-based idea is we can argue that it's a general approach that can scale up FPT algorithms. And then we first show that let B be the budget, let L be the maximum attack path length. And we show that our problem is W1 hard with respect to the budget, even for a constant maximum attack path length. And then this is proved based on showing that the optimal blocking is as hard as finding a click. Okay, I'll skip over the details. And then our first fixed parameter algorithm is actually very sort of like a straightforward. So the idea is like this. If besides assuming a small L, small maximum attack path length, we also assume that both the budget and the number of entry nodes are both small, then we can actually easily just use a bounded width tree search algorithm to find the best solution. So the idea is that we can randomly select one entry node, and then this entry node, we just find an arbitrary shortest path from this entry node to the main admin. And then we have to do something on the edges along this shortest path. And then if we need to choose one edge to block, there are L choices because the number of, basically the maximum attack path length is at most L. That's at most L choices. Or we don't touch this shortest path at all. And if we don't touch this shortest path at all, then for this entry node, we can actually ignore it because its shortest path to domain admin is not affected. So at the end of the day, when we calculate the average success rate for the attacker, that entry node can be put aside. Okay, so essentially we would have this kind of recursive relationship, as in we use CBS to represent the number of combinations that we need to consider in our fixed parameter analysis, where B is the current budget, S is the number of entry nodes, and then this is equal to L times CB minus 1. So basically, if I need to spend my first unit of budget, I need to basically select one of the edges on the shortest path from the selected entry node to domain and mean. So that there are L choices. Or I don't touch that selected entry node at all, and then that entry node can be removed. So it comes down to S minus 1. So we have this recursive relationship, and then there are some base cases. I'll skip over that. And then at the end of the day, we have this, the total number of combinations is like this. And then for each combination, the complexity is linear, all right? So there's some analysis on why each combination is linear, but I think I'll probably skip over that part as well, just to save some time. And then our second algorithm, because I want to save some time to get to the graph neural network part, okay? So our second algorithm is based on tree decomposition. And as I mentioned earlier, for those of you who are not familiar with tree decomposition, the tree decomposition and similarly, I'm sorry, not similarly, and correspondingly, the idea of tree width, these are commonly used definitions to describe how close a graph is to a tree. And many computationally difficult problems on general graphs turn out to be easy if we focus on graphs with small tree width. That would be graphs that are very close to trees. A small tree width means the graph is close to a tree. And this is also the case for our problem. So here on above is the example attack graph I just showed. And below is an example tree decomposition of this graph. So you can see that I actually convert this graph, which is not a tree, into a tree. But the difference is that the nodes, the tree nodes, are no longer single vertices, like a single vertex. The tree nodes are, we sometimes call them bags. The tree nodes are bags of original graph vertices. Okay, and then the definition of a tree decomposition is that you want to create a tree where every vertex appears at least somewhere, and also for every vertex, for example 3, it appears in here, 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 and here. For all the bags where 3 appears, the bags should form a subtree. And another requirement is that for every edge, so for example 1 and 0, for this particular edge, both ends need to appear somewhere in one bag at the same time. So 1 and 0, it need to appear somewhere in the same bag. That's the definition for tree decomposition. Now that's a fairly complex definition, but then the high level idea is essentially like, why do we care about like this tree decomposition? What's the whole point? The whole point of tree decomposition is just that every bag is actually a separator, in the sense that if I remove everything in the bag, so for example, here in this bag, 3, 1, 2, if I remove 3, 1, 2, it would cut off one side from the other side. So for every bag, I have the same property. So for example, if I cut off, so this is probably the best example, okay? So if, for example, like a 102, if I cut off 102, but then it's one side and then the other side is actually empty, all right? But then for this particular bag, if I remove these 3, then it's one side versus the other side, they're both not empty, okay? So why do we care about this separator? We care about this separator because this actually can form the basis of a dynamic programming algorithm. The dynamic programming algorithm goes like this. We would start from the bag containing the domain and mean. And then we would basically decide, for example, how I should block the edges related to the domain and mean, and later on, how do I block the edges related to 2 as well? How do I block the edges related to 1 as well? and then etc. For example, suppose after I make the decision at this point, so after I decide how to block for 3, 1, 2, after I decide the distance, the final distance for 3, 1, 2 to the domain admin, after I decide that, because this is a separator, so essentially I'm facing 3 independent problems now, because if I remove this, then they are basically cut into separate parts. So these 3 parts, they are not related anymore. I can make independent decision. And then similarly, after I decide the distances from 3, 1, 2 to domain admin, I don't really need to keep track of which edges I have blocked along the way until I reach here. That can be forgotten. All I need to keep track of wouldn't be for every vertex in the bag, what is the distance after my blocking? And then that's the only thing I need to keep track of. And then that basically the amount of scenario is limited because I'm assuming that the maximum path length is small. So the possibility in terms of distance for every vertex is small. And then I'm assuming the bag is small because the graph is supposed to look like a tree. If it looks like a tree, then the bag is small. For example, we're talking about like 5 nodes or something like that, but basically a bag size of 5. And then that would be basically maximum attack path length raised to the power of 5. And then that would be the total number of scenarios I need to keep track of in the dynamic programming algorithm. All right, so that's why at the end of the day, we can come up with a scalable algorithm. All right. So the optimal tree decomposition that actually minimizes the tree width, minimize the maximum bag size, that is actually NP hard to compute. So basically, that problem in itself is difficult. And then there are known heuristic. One heuristic is called the vertex elimination. And then the vertex elimination heuristic essentially says that you need to specify an ordering of the vertices. And then once you specify an ordering, all you need to do is just go over the vertex one by one. And then for each round, you just eliminate one vertex by creating a bag containing itself and all the neighbors. And then you also fill in missing edges so that the neighbors would form a clique. And then the way to connect the bags together is just like given a bag X, let Y be the earliest bag created after X according to the ordering, and that X and Y shall some vertices, then X is attached to Y in the final tree. So basically, we have a heuristic for generating tree decomposition, but then this is only a heuristic because we don't know the optimal ordering. If we know the optimal ordering, we are solving this NP hard problem, okay? And here in this paper, we use a very specific ordering. We basically look at this AD graph, and the ordering we pick is that we basically treat the domain and mean as basically the node that belongs to the highest security layer. So essentially what we do is just that we assume the graph is acyclic. And after we assume the graph is acyclic, we can basically do the topological sorting. So for example, for this graph, topological sorting is very straightforward, right? Like basically these 3 followed by this one, then followed by these 2, then followed by this one. So they would form multiple security layer, most secure layer, second, third, fourth. And our vertex elimination heuristic is based on the ordering where I would eliminate this one first, then this one, then this one, then this one, then this. Basically, I just eliminate the vertex according to the security layer, according to the result of the topological sorting. Okay, so basically that's how we generate tree decomposition. And one thing I haven't really mentioned is that, okay, so well, before I talk about that, it's just if I use this heuristic, then it would actually create a tree decomposition that I call the desired tree decomposition. And I call it desired because it actually has a few other features that make the dynamic programming more convenient. Okay, so basically, we assume the graph is acyclic, then we can use topological sorting, then we can create a tree decomposition, then we can run DP. And the one thing I haven't mentioned is that just what I said just now, I was trying to convey the idea, basically the high-level idea, and I intentionally left out one piece of important detail. The detail is that actually when I make our DP, basically, for example, I mentioned that if I decide the distance from 3, 1, 2 to domain and mean already, then basically the 3 following branches, they would be independent. Okay, that is actually not true. That is actually not true unless we assume that the graph doesn't contain cycles. So here, if there are no cycles, then indeed, what's happening in the different future branches, they are independent, and that's needed for the dynamic programming algorithm. If it contains cycles, then I cannot guarantee that, and then the dynamic programming algorithm would fail. So basically, the dynamic programming algorithm proposed in this paper is more like a heuristic because we need to assume that the graph is acyclic, even though indeed, I mean, according to our experiment, the synthetic active directory graph indeed look very close to being a cyclic, which is something I will talk about. But then we already addressed this issue. We already figured out a way to do dynamic programming that handles cycles. That's basically part of the extended work from this paper. Okay. And now our third algorithm is, we call it a SPLITFPT. And then here we basically use a very, how to say, maybe it's an interesting idea. So essentially, like, the observation is that for each defensive setup, a set of edges blocked, there's a corresponding optimal attack plan. So after I set up the blocked edges, the attacker would basically attack via the shortest path. And then we assume the attacker is just doing this best response. And then basically, the defensive strategy space is huge because we need to choose B edges to block from tens of thousands of edges. And that is a very large search space. But on the other hand, the attacking strategy space is actually very limited. Because if the graph is close to the tree, then the only decision, only basically choices for the attacker is just to figure out what he should do at the splitting nodes. The splitting nodes are basically nodes with multiple outgoing edges. If a node has only one outgoing edge, the attacker can only go via that edge. There's no choice. And the attacker needs to make a choice only if there are multiple outgoing edges from a node. So if the graph is close to a tree, then the number of splitting nodes is going to be limited. And then if the number of splitting nodes is going to be limited, then the attacking strategy space is very limited. So essentially, we observe that attacking strategy space is much smaller than defensive strategy space. So how about we just, instead of doing first search for a good defense, then check what's the corresponding attack plan from the attacker, and then go back, adjust the defensive plan. We don't do it that way because that will be facing a very large search space. We do it in the other way around. This is just like, this is, for example, like for bi-level optimization, it's like flipping the min and the max, right? It's very similar to doing something of that kind. But then what we are doing here is just that we go over all the possible attacking strategies. One of them must be the correct best response to the optimal defense. So what we need to do is just that we perform fixed parameter analysis on the attacker's strategy space by going over all combinations of the attacker's choices at the splitting nodes. And if the graphs are like trees, then the attacker's strategy space is much smaller compared to the defensive strategy space. And then for each attacking strategy, we analyze what kind of defense would make this strategy a valid best response. Because we are going over all attacking strategies. One of them must be the best response to the optimal defense. Okay. So we just do a for loop with the attacking strategy. For each attacking strategy, I just pretend this is actually the best response to the optimal defensive plan. And then because the strategy is now given to me, is already fixed, I can figure out the corresponding defense. I can figure out what kind of defense would actually induce this kind of attacking strategy. So basically, if the attacker is using one route, then we cannot block it. Otherwise, the attacking strategy is not a best response. And if the attacker is not using a route that is actually shorter, we must block it because, again, otherwise, the attacking strategy is not a best response. So basically, we go over the attacking strategy one by one. For each one, we pretend that, okay, this is indeed the best response to the optimal defense. If that's the case, what would be the defense that would induce this attacking strategy? And we can figure out that defense. So one of the defense we figure out at the end must be indeed the optimal defense. So essentially, that's the plan for this fixed parameter algorithm. Okay. And then, as we mentioned earlier, this SPLITFPT is based on an interesting idea, but unfortunately, the search space is huge. But on the other hand, this search space is very similar to a node classification problem because we are searching over the attacker's strategy space, and all we are searching for is that when the attacker faces a splitting node, which route the attacker would choose. That's basically the kind of thing we are searching for. So that's a node classification problem. Given a node, we classify which route the attacker would go to under the optimal attacking strategy facing the optimal defense. So it's a node classification convolutional graph neural network take one splitting node as input and output its classification. So for example, which route the attacker would take when facing the optimal defense, it's essentially guessing work. But then that's what neural networks do. And so we given the current neural network, that is the current node classification rule, we randomly flip some nodes classifications and check whether the perturbed classification leads to a worse success rate for the attacker. And if so, we instruct the neural network to update the model weights to learn toward this better classification. So we treat the better, basically, we perturb the classification, and if we found it basically better classification, we treat that as a true label. So basically, this is unsupervised learning. And then the goal is to get a small number of node classifications correct and hope the neural network is able to pick up the underlying rule and then can help generalize to produce correct classifications on all nodes. Okay, so that's basically how we combine graph convolutional neural network with a fixed parameter analysis. And then in terms of experiment, an organization's Active Directory attack graph is considered sensitive information. It's extremely difficult to find real AD graphs. Actually, we don't even have any. Even for the University of Adelaide AD graph, we have part of it only. Okay, so we conduct all experiments using synthetic Active Directory attack graphs generated by BloodHound team's synthetic graph generator tool called DB Creator. And we look at a few different graphs. One is called R2000, where we set the number of computers in the organization to 2000. And then the final graph would contain nearly 6,000 nodes. And that will be computers, user accounts, security groups, all combined, and then 18,000 edges. And then another one is called R2000 DAG, a cyclic version. So essentially, we make R2000 a cyclic by removing 4 nodes from it, which are the only 4 nodes causing cycles. As I earlier mentioned, that one of our 3 fixed parameter algorithms actually requires a cyclic graph. So to make the graph a cyclic, we need to remove 4 nodes. We can argue that the IT admin can throw in additional monitoring resources on these 4 nodes so that the attacker is not going to attach them, not going to touch them at all. If that is the case, then the graph is a cyclic and we can apply all 3 algorithms. Otherwise, one of the DP-based tree decomposition-based algorithm that can only be considered a heuristic instead of an exact solution. And then in each trial, we randomly pick the entry nodes and randomly set some edges to be blockable, and all experiments are repeated 10 times. The first experiment is a low budget setting, and in this setting, we are able to run our first FPT algorithm, budget FPT, that requires a small number of budget. And so basically, we set a budget of 10, set a 5 to be the number of entry nodes. And then we get the optimal success rate. The optimal success rate is 30% on average over 10 trials. And then using GCN, we got 32%. Okay, that's fairly close. And then there's another greedy algorithm that is really bad, 48%. The greedy algorithm essentially goes like, if my budget is 5, then I would spend my first unit to pick the edge. That would maximally decrease the attacker's success rate, and then keep doing that for 5 rounds. And then here, number of OPT means out of 10 trials, how many times this algorithm is actually optimal. So for out of 10 trials, GCN is actually optimal 9 times. There's only once that it is not optimal. And then for greedy, there's only 1 out of 10 trials that is optimal. Okay. And then we experiment with our DP algorithm that requires a cyclic graph. So we run it on R2000 DAG with 10 as the budget and 5 as the entry nodes. And then for DP, we can run DP now, and we get the exact optimal solution. We can run GCN, we can run greedy, and then it turns out that they are all producing the optimal result. Every trial, out of 10 trials, they are all optimal. Okay, so we then made a spin on this cyclic graph. Greedy actually is not going to be optimal, because if we go back to the earliest example, if I use greedy algorithm and my budget is 2, and I would block 2 out of these 3 edges instead of blocking these 2. I'm not blocking these 2 because if my budget is, for the first budget, if I block this one, that doesn't even help because the attacker can go via the other one. So that's why these 2 are never picked by greedy strategy. These are substitutable edges. So essentially, this can model a scenario where from one node, there are 2 separate exploits, 2 different ways to hack into future accounts. So that would be the basically the substitution edge structure. If we throw in this kind of structure to our experiment, and we basically throw in some structures like this, then greedy would fail. And then GCN still produce the optimal result 10 out of 10 trials. And then finally, we look at a setting that is larger where we cannot run any of the fixed parameter algorithms. So we have a budget of 20, we have a number of entry nodes to be 10. And then remember, we are talking about like really large graph, like 6,000 nodes. Okay, and then it turns out that, and then another parameter we set is what is the probability that an edge is blockable. So whether it's 20% is blockable or 40% is blockable. And then when it's 20% blockable, the success rate of GCN is actually worse than greedy. And then after looking into the result, we figure that, okay, that's because the number of, basically the good edges are very rare. So because the chance of an edge being blockable is smaller. So the block-worthy edges are relatively rare, which means that the greedy, even though the greedy is unwilling to pick substitutable edges, at the end of the day, they still pick those. Because the budget is 20, we can pick 20 edges. And so if we adjust the probability and change it to 40, then the block-worthy edges are a lot more. And then in that case, greedy wouldn't be really bad, once again. And then the GCN wouldn't be better. And here the number means that out of 10 trials, 5 times GCN is better. And then the other 5 times GCN is basically tied with greedy. And then here, out of 10 trials, 3 times greedy is better. Once GCN is better. For the remaining 6 times, they tie. Okay, so that's basically the last experiment. In conclusion, we proposed 3 fixed parameter algorithms based on the practical structures of AD graphs. And then one algorithm is extended using a graph convolutional neural network heuristic. And our algorithms scale to handle AD environments with thousands of computers by exploiting the special structures of practical AD graphs. And our algorithm will help IT admins to identify high-risk edges, excesses, exploits in practical AD environments. And some of our techniques are potentially useful for other models, such as performing FPT on the attacker's strategy space when the attacker's strategy space is much smaller than the defender's strategy space, and also using neural network to search, basically to scale up FPT algorithms. All right, so that's it for my presentation today.